Hello, everyone, and welcome to today's graph reading group.
Where we have Jonas Köhler telling us how to do normalizing flows on rotations.
I'm Jonas. I started in January working at Microsoft as a senior researcher. So I did a PhD on mostly generative models for sampling. So today the presentation of the paper is also very much related to that. So mostly sampling of proteins, but yeah, generally any kind of molecular systems. My background is a mix of math and computer science in my undergrad, and then master in machine learning in Amsterdam. And so my background is not chemistry or physics. This I had to learn the hard way. Now at Microsoft, I work a bit on different stuff. Nowadays, I work more on deep quantum Monte Carlo, so like solving the Schrödinger equation using deep learning tools. So general research interests are generative models, equivariant neural networks, and of course solving physical problems with deep learning tools.
That's what I like.
Today, I mean, as you know, I will present our most recent work, the rigid body flows. And so in preparation of this, I was a little bit thinking that there are so many prerequisites that you should probably brush over in order to really understand why this is a paper. But I don't know what's the background of the audience. So if everyone is by certain stuff that I brush over, then please shout, and then we can just quickly skim over that. So
but we all assume that we've read the paper, and there will probably be questions about the paper, but we've read it, and we can ask for clarifications where the things are unclear.
So do you like to go through the paper, or because I prepared a bit of so just to give you an idea, a bit of a talk. So the idea is basically giving some of the motivations, then the technical apparatus, which I think is the core of the paper, which in my opinion is not so trivial because it involves all the technical details of, I don't know, flows and manifolds and these kind of things. And then just quickly talk about applications.
So I would quickly try to do the motivation quick, because I think we had many papers like this in the reading group already, and know the sampling problem and so on, and know what Boltzmann generators are. But then I think we will have to spend quite some time on our quaternion diffeomorphisms and
this is what I anticipated, right? Okay, maybe then let's just dive in. So in general, so this is something I guess you already know. So molecular conformations. So if we have two proteins, so the nice ramen noodles here. So let's say it's the same protein, but in two folding states. And then, as you already probably know, that molecules are not just single structures, as there are these structure prediction tasks, or I don't know, small molecule generation tasks, but actually you look into a whole energy surface, and then like what we see as a single structure is just a snapshot, like a single point in this continuous surface. And then if you talk about a state, we talk more about like a basin of things wiggling around here and wiggling around here, and sometimes there are transitions happening. So just this is important because sometimes in the machine learning world, this is not super clear. And then there's the Boltzmann law that tells us something about like if we sample, like let the system here, for example, run for infinite time and just walk around in the potential, then we can basically use the ergodicity theorem. And then there's this nice statement that the time averages converge to ensemble averages. And what it means is that given from this potential, and we run just the classic Hamiltonian dynamics, the whole thing will converge to the Boltzmann density, which is given by the known form here.
Jonas,
so,
can you switch your pointer to the white pen or something such that we see it better?
I can try.
Do we actually see it better then?
Yeah, that's the question.
Or maybe if you point to something, you can just paint in white and then Control Z. I don't know.
Okay, let's try that. Okay, good. So so I talked about the two states, then here about the potentials, right? And then the ergodicity, like if we just move around here, hit back and forth, for an infinite amount of time. In the end, we get a density of states that follow this Boltzmann density here, which follows the known law of being distributed to the exponential minus u, where u is the potential. So just basics. All right, and then a very important quantity that people are usually interested with these kind of Boltzmann densities is the so-called free energy or the free energy difference.
Can I just make a comment here on the Boltzmann density? Yeah. Just because we're talking to a machine learning audience, the Boltzmann distribution is basically the softmax of the potential, right? So in general,
yeah,
like
if you want to take a softmax over a non-countable set, then yes.
Yeah. So and in many cases, though, we treat a countable set of like local minima when using the Boltzmann distribution. But in other cases, yeah, we consider like non-countable sets. So just fun fact, softmax appears in physics, and this is where it appears.
Yeah, I mean, you could also phrase it, in my opinion, makes more sense to phrase it the other way around. You can basically say, generally from ergodicity, you end up with a Boltzmann type distribution. So basically the classic thermodynamics. And then if you also apply this to discrete states and use other kind of transitions, I don't know, Markov chain transitions or something like this, then in a discrete state, you end up with a softmax over this discrete space. And I mean, if you take the integral for the C, the partition function, then of course, you can also write something down like a softmax in continuous space. It's just like there's no easy closed form or something like this. It's not that we can write down an operator like in a softmax sense. But I mean, yeah, the analogy is the same. I think in machine learning, I think it's just, for me, the usual analogy that I make is basically this whole field of energy-based models or EBMs, which exist much longer than the recent applications to chemical physics, where people pretty much develop the same machinery independently of what the people in chemical physics did. So there's another connection. But yeah, just different names for the same thing.
Brad has his hand raised, so Brad, maybe you can speak.
Great, thanks. So I'm really looking forward to this talk, but so maybe you're going to cover this, but my first comment would be that don't we have ergodicity breaking in protein structures? I don't know that I would expect them to have long time ergodicity.
I mean,
because,
let's say like this, if you assume your protein to be distributed according to the Boltzmann density, you already assume equilibrium as such. This is basically the definition of equilibrium as such ergodicity.
So sorry, just to push back on that devil's advocate type thing. If you have a protein doing, sorry, you probably are sick of these questions. I'm sure you get them all the time. If you have a protein doing catalysis, that's, you know, those fluctuations are not ergodic. That would be ergodicity breaking, right? So for most proteins,
it depends on what's your system or like the state. If you say you put everything in a closed box and then things happen in that, and you, I don't know, have an isobaric ensemble where you keep the pressure constant, or isothermic ensemble where you keep the temperature constant, or whatever, keep things in a fixed box, and then you run simulations on that without basically changing the total energy. Then you end up in something that's in equilibrium. In this case, you have the Boltzmann density follows. But of course, once you go to systems that are open, where you, I don't know, add or take away energy or whatever, then of course this can't hold anymore. And so depends really on the specific system you concentrate on. If you look at basically a system like a protein and body temperature and water and just wiggling around, then this kind of law describe it pretty well. But of course, it's a total fictitious case.
So okay, I get your comment, and thanks for addressing that. I'm just thinking in the biological case, they're certainly not ergodic, and when they're doing their, you know, and
this is true. But I mean, if you assume that everything is connected in the body, and you have to look into all these confounding exogenous variables, then it becomes pretty tricky to model anything.
Sure. And we're getting far from from what we're studying. Okay, I'll put my hand down. Thanks for the discussion, though.
I don't know, but yeah, this is a good reminder to maybe keep in mind that not just about like, right, we're modeling a protein here, so it just makes it does make sense to have our Boltzmann distribution here, but that maybe in our body, that's even the sort of data that we have from crystal structures or things like that. The proteins might just look quite different or behave quite different than what we have in our models, because there are all sorts of things that we're not modeling.
But in general, I think one should be quite careful about this. So I'm far from biochemistry, not leaning out too much out of the window now. But so from a mathematician's side of view, I would say we usually just model something, which means we define model boundaries.
Sure, but
within the model boundaries, we can make predictions. And then the next step would be taking these predictions and match them with experimental data.
And now our model is this system. We have our force field or our energy function that describes our system. It's maybe this system does not perfectly capture everything that's going. It doesn't, because there are additional things and connections. But yeah, let's continue.
Yeah, this is great. So that's perfect to have a framework to start from. I just wanted to make sure we do a good job.
That's clear. Yeah, sure. So whatever we do in physics, math, I mean, economics, I don't know, is always you define your model boundary, and within the model boundary, you make predictions, and then you can see how well they match reality. Yeah, we can't do much more than that. But apparently it works pretty well. And I feel like people use this quite often, this equilibrium assumptions for a lot of things.
Let's do it and let's continue. All
right. So, okay. So important quantity that we usually study here is the free energy, or more importantly, the free energy difference. And so as said before, like if you look at the protein state A and B, as I said, the two axes here are not the state, but rather basically the whole surface here. And then we can look at the whole probability of the whole thing. And then, as you might remember from probability class, so there's a density, and the actual probability is the integral over a volume. So what we look into is basically the probability of state A or state B. And then the free energy of a state, A or B, is very simply defined as the negative log probability. So if you think about machine learning, we can basically say it's kind of the likelihood of a state if we discretize the space into these chunks here, A, B, C, whatever. And the free energy that just describes, you could say, the normalizing constant if I want to turn this into like a local density. And the interesting thing that we want to look is, like, usually you don't care too much about the whole normalizing constant. This is kind of difficult to estimate. What is easier to estimate, also much more interesting in many cases, is the relative normalizing constant. You could basically say the probability going from one state to another, or the stability of the state. And this is the difference between the log probabilities, you could say. And this quantity, so if F is the free energy, then this delta F is called the free energy difference. Pick another color, it's easier to see then. And yeah, so the free energy difference is interesting. As I said, it's more kind of like a likelihood ratio or something like this from a Bayesian perspective. But what does it tell us? It tells us, if we look at these states A and B, it tells us, for example, how stable is the state? Does the transition happen between them or something like this? Or for example, if you have a state of a protein in a truck, you could, another way the truck binds, you could ask the question, will the truck bind or not? Okay, and the problem with this quantity is simply that we have to sample the Boltzmann distribution in order to actually evaluate these kind of integrals, or the integrals that pop up here, right? And yeah, this is the actual challenge, super hard. And yeah, so the traditional way of sampling is molecular dynamics. So one of the easiest way to write it down is just using Landau equation. So we have a state, and then we do a little tiny gradient push, and we add some isotropic noise. No, I did something stupid. I hope it was okay.
All good. We were talking about our MD and how we
Yeah,
do
no, I deleted something, but now it's back. Okay. So, and the problem with the MD, the nice thing, so if epsilon goes to 0 and we have infinite time step, we just know it samples the actual thing. And this is actually the ergodicity we talked about. Then we have a problem a bit in practice because for many systems, especially like if water is involved, where atoms shouldn't clash and so on, we need really, really small time steps. So usually in the range of femtoseconds. And as such, the convergence of this whole thing towards the equilibrium density is extremely slow. Like as slow that Frank, my PI, usually says, so 2 PhDs in classical MD, like people doing, I don't know, analyzing certain protein and looking for folding pathways and such, consumes as much energy as one Saturn V rocket start. So this is roughly the ballpark of energy consumption that you need for the computation. And yeah, so this is just not really scalable for whatever we are interested in. But so far, it's the only, let's say, ground truth method that we have for most of these things. And yeah, usually practical problems are you just don't know when it was actually converged. I mean, you just have trajectories and yeah, a lot of them, and you just don't know. Maybe you just missed a state. So there are a lot of practical problems, but at least theoretically it's super principled. And yeah, so since then, of course, deep learners also looked into this, and there are a bunch of works, some of our groups, some of other groups, trying to actually leverage neural samplers for this problem. And I will just briefly go over the two of them. We just heard about Boltzmann generators were discussed already, but
sorry, like just to add here, like you mentioned that it's very slow. Could you slow to converge? Can you explain a bit like the reasoning of why it's so slow? For example, like is it because it's stuck in local minima? Like what's
I mean,
tell us
so
a bit more about that.
Frank's usual example is that you say, I don't know, you have like a protein complex. Here's my crappy drawing. So you have a protein complex that could bind to each other or unbind. And then basically this process, this happens fast. Like, I don't know, something in milliseconds or what. Oops, milliseconds. Sorry, my writing is bad. So this is milliseconds. But the unbinding process can be like seconds to hours. Yeah. And the problem is with the small time steps. So in order to not make any mistakes here, so like because this integration is only correct if we go to the continuous limit. So we have to make super small time steps to not accumulate integration errors. And so what you have in MD is usually 1 to 4 femtoseconds. So these are like, I don't know, 12 to 15 orders of magnitude away, which gives you a lower bound of the amount of steps. You need to just observe one of these transitions. So it clearly tells you basically how much limited you are in modeling actual systems.
And the reason here that it takes so long to go out is probably because it's a local minima of energy that is much lower than the free molecules, right?
You could say that, or I mean, it's even worse, I'd say. It's more like, let's say you have like a probability Poissons that are not so far off, actually.
Yeah.
But the problem is there's just one, like this is super high dimensional, and there's just one super narrow funnel that actually makes this transition because, like, for example, you can't violate hydrogen bonds, or you have to avoid atom clashes, or whatever. So basically nearly all possible moves that you could go from A to B are basically forbidden.
Yeah.
And then these are actually not too far off. This is the annoying part, just that everything else that you go is basically always exploding, which means you have to basically be very lucky to actually go into the direction of where something happens that you're interested in.
Yeah. And actually, one good analogy that we can have here is suppose you have a human who's in a local minimum of energy standing, and that same human, where when sitting down on a chair is also at a minimum of energy, but then the transition state where that human is like squatting like that is a high energy system, and the human has difficulty transitioning between these. That's one thing, one analogy that we can view between that. So like, yes, your low energy standing, your low energy being sitting down, but transitioning between the two requires you to make a move.
Yeah, but the annoying part is it's not only that the barriers between the bosons are high, it's also that there is actually a pathway. This is what people usually try to study or to find.
Yeah.
But this pathway is just so narrow and so hidden in the whole mess of, I don't know how you have to actually wiggle around all these parts. It's just extremely hard to find.
Yeah, exactly. Another thing I'd like to mention is that molecular dynamics also requires some tricks, because like suppose you start with this system that you described here where you have the two proteins, right? And you do just a naive empty simulation. Well, this one might go in that direction and the other one might go in that direction, and they never bind because the movement are totally random. So it also requires some domain knowledge on how to guide the molecular dynamics so that they the proteins actually join together, right? So it's not as straightforward as just like hoping for the best, because then anything can happen.
But this is what I meant by the slow convergence, or like the question, did it converge at all? And this is like a lot of black magic. Like, I don't know, you set up your simulation and there's a lot of, as you said, like domain knowledge and I don't know, looking into known transition paths and studying like how much is basically, it is a converged on this transition path or whatever. But I mean, if you have an unknown system, it's still like random search. So this is one of the big problems with MD, even though theoretically it's so nice. But yeah,
okay, but keeping the bigger discussion picture in mind, if we go at speed, then we'll never get to our normalizing flow quaternion modeling.
Yeah, I just wanted to say I wanted to go to the next steps. So to remove that. Yeah, so if we go to the next step, so we thought about Boltzmann generators, which is the idea using normalizing flows or any kind of tractable probability model, sample a simple density, push it forward using this flow or stochastic map or whatever, and then use reweighing techniques in order to estimate expectations like the free energy difference. And very analogous is the work from DeepMind, so-called learned free energy perturbation, super similar. And I just mentioned it because we used it in this work, which is you run a simulation for one energy, for example, for a high temperature energy or from a different system, call it U0. And then similar to what we did in Boltzmann generators, you learn a transport map, which maps basically this first Hamiltonian on the second Hamiltonian. And then you can use this to estimate the free energy between two states. In this case, these are thermodynamic states, so not states of folding or whatever, but for example, the state of having temperature 1 and temperature 2. Yeah, so these are the applications. And now the challenge with this in practice. So far, like what here they usually only did like bulk water. So basically water was seen as a single atom, and then basically you look at the box of it and stuff happens there. And here we just had like toy systems and small proteins, but without water. And the question is, of course, like how do we actually tackle the real water? Okay,
but still as rigid bodies, right, in your work.
This is what I wanted to talk now. Yes. So let's look at the left picture. So we looked at the protein, and then the little blue things around, this is the water. And if we zoom in, actually water is not just a dot. So water is basically made of two hydrogens and oxygen. And in most water models, we basically assume that the angle between the hydrogens is fixed, as well as the distance between oxygen and hydrogen. So it's of course not perfectly fixed, but you could say for all reasonable approximations in MD, it's called fixed. And many MD algorithms in the simulations consider that because it makes computations a lot faster and also numerically stable. For example, one famous is shake. It's just one way to actually constrain your update steps to always stay in this manifold of constrained rigid bodies. But if you look at it from a probabilistic perspective, then you actually have a singular density because we describe our system in the full XYZ coordinates. In this case, for one water molecule, it would be 9 degrees of freedom. But the actual degrees of freedom that we can move into are just 6 degrees of freedom, which are given by the rotation manifold and by the translation of the system. Which means we have a 6-dimensional density, which is actually embedded in a 9-dimensional space. And this is something that's tricky, because if we now look for a likelihood solution, it looks a little bit like this. So if blue is the model density and red is the target density in the singular manifold, then we have something like a delta spike and we try to fit a Gaussian close to it. So it's totally clear that we have a lot of mass that we don't miss. And we get really, really poor fit, because if you go to many, many high dimensions, pretty clear at some point you just sample garbage. And if you do reverse KL training, so you just do the energy-based training of a Boltzmann generator or whatever, or the free energy perturbation loss, then this is simply none, because then you're sampling from the blue one, but here the density is 0, so it's just infinity. So yeah, we need a way to actually think about how do we model this implicit density in the 6 degrees of freedom within this 9-dimensional space. And yeah, so in order to do this, we thought about, okay, we can actually basically remove the problem if we say we start with a all atom configuration, which is in 3 by 3, so 9 degrees of freedom. And then we transform it into the rotation, the translation, and then inner degrees of freedom. In water, it's just an angle and 2 distances, but could, in principle, if you have larger rigids, can be anything that is then expressed in an internal coordinate system. And so far, so easy. So we can say we just keep them fixed in a flow. We don't do anything with them. And we just modify this with the usual coupling flow or whatever. This is just a Euclidean 3-dimensional variable. Yeah, then we still have the problem to actually tackle this guy, which is element in the rotation group, SO3.
Jonas.
Yeah.
So someone in the chat is asking now, why not model the 9-dimensional space directly?
Because if we do this, then we are back to this case.
Yeah. Like the thing is that we have that our degrees of freedom basically are 6-dimensional, and this is where everything is happening, and the other 3 dimensions, they don't matter. And the density is always the same no matter what we do in the other 3 degrees of this three degrees of this degrees of freedom. And yeah, that's why we end up with this singular, or this manifold where there's only support, or this distribution where there's only support in a tiny sliver.
Yeah, you could also say, like, if we have a density on 2D, but where we basically just have everything concentrated on a circle and strictly on a circle, then it's super hard taking a 2D density and make it fit perfectly, because we will always have mass around the circle and their energies will be infinity. And this is a similar thing here, just much more complicated, much more high dimensional. This is why it's a terrible idea to go to 9-dimensional systems and hope to match the density there, because the tails, they will be totally off. And you will have this for 3 times, you have this for n different molecules. So this quickly explodes into nonsense. So you can try this, but I'm very pessimistic about this approach.
All right, how do you do your rotations?
Exactly. So the question is then, how do we tackle rotations? So the question is more like, if you have a flow, as I said, like, we can keep those fixed, we can do this as usual, but then the big question is, how do we do actual rotation flows? And this is the core of this paper now. So first, quick recap on normalizing flow. I try to keep it quick. So normalizing flows is the idea that you have a base density, like a Gaussian. You have a diffeomorphism, so an invertible map that is differentiable. And you try to match a target density, in our mu here, as close as possible with the so-called push-forward density. And the push-forward is basically given by the change of variable, that if you spell it out, looks like this. So you have the pullback along the flow and the base density, and then you have this Jacobian of the transformation correcting your density. And if you have such a normalizing flow, the nice part, why we care about it, what you need for this line free energy perturbation and the Boltzmann generators is that you can then do reweighing, which means like you can compute for each sample that you take, you can compute the target energy, you can compute the model density, and then you can use self-normalized importance weighing or other stuff to actually get an unbiased estimate of any target observable. So this is just for context. Why do we care about flows? Why not we use diffusion models or GANs or whatever? Okay, so now to the technical parts. So first we have to look at manifolds. So just a recap, I try to keep it simple in this talk, so I just brought it down to submanifolds. So if we say we have an m-dimensional submanifold of an n-dimensional space, this usually means we have a subset in Rn, which has the property that locally around each point P of the subset, there is an open set U called, yeah, basically like a, of course, what is it called usually? Yeah, let's call it just open set. And so there's an open set U, so that we have a local function kappa, I call it kappa, which is a chart from this U to some real vector space. For example, if we have the circle, it means around each point on the circle, there's just an open area. If we just cut it open here, that is locally homeomorphic to the real line. So this is just a general property of a manifold.
So that means for every point, there needs to exist an open set such that there is a one-to-one map to
like a smooth diffeomorphism to a real dimensional, a real m-dimensional vector space.
Okay.
Yeah, and this then is a m-dimensional, so corresponding to the submanifold, to this chart, an m-dimensional submanifold of Rn. So the circle here would be R2, and this is R1.
And your chart is just your diffeomorphism.
Yes. So then the next thing that we have to look into is what is the density on a manifold. This is not so clear, I think. So the easiest way to look at this is basically looking into this chart formulation. So if we say we have a density on a circle that's embedded in 2D, then we've said before it's singular, right? So it's basically infinite if you are on the circle and 0 outside. But you can make this better if you basically use this property of the manifold and say, okay, I have this local point, I have this local environment, and I can go back to the real line. And the real line, we just know how to define a density. So we can also say that we just define our density on the real line, which is then just a traditional density. And then we define the density on the manifold over the pullback construction. So what we do is basically we say the point P, where we evaluate the density on, is just the density of basically on the real line going through the kappa. And then again, we have something like a Jacobian term contributing like a normalizing flow. Just it gets a bit more complicated because now our chart is not full rank anymore. So here we go from R2 to R1. So this Jacobian now becomes an m by n matrix. And so itself, there wouldn't be a well-defined determinant, but what you can do is you can take the determinant of the so-called Gramian. So it's basically Jacobian transpose Jacobian. And then this is a full rank matrix. From this, you can take the determinant. And then in the end, you have to take the square root of it, which is the more general Riemannian formulation of the normalizing flow equation that we saw before. So this is how you define the density on the circle now, basically chart-wise by densities on the lines.
I'm confused now.
Okay.
So we have our two-dimensional space. We map to a one-dimensional space. So
locally, yes. Mm-hmm.
Locally, okay, and that's why we're not saying that it's. That's why we're still saying it's a diffeomorphism.
Yes.
Like one-to-one.
If you think about the circle, I mean, I can always, for example, cut the circle open at one point and then take each part, right? But then it's not fully diffeomorph because I have this cut point.
Okay, but the Jacobians of our kappa are still not square matrices, and because we go to a one-dimensional space, And yeah, no, I think I'm happy now. But maybe oftentimes it's not so easy to get. Getting the Jacobian over kappa.
It depends on the manifold. If it's an unknown manifold, it's complicated. But of course, if you know the manifold well, then the charts are known. Then this Jacobian is not so complicated to get. Depends.
Yeah.
For the circle, it's pretty clear. I mean, the Jacobian is literally just the tangent vector that you get, more or less.
Yeah. And in the chat, Professor Olsen is asking, but how is it full rank?
So this thing is full rank. So in this concrete example, it would be just a 1-by-1 number, which I think usually has if it's not 0, has a useful determinant. And in a general case, it's just the charts. In order to make sense, the charts are always full rank on its image, so the M. This is just by definition, because we already said the manifold is M-dimensional. This means like it's always.
Okay, but did you just say that the manifold is M-dimensional?
So I said before, there's an M-dimensional submanifold of Rn.
Okay. Yeah, so N is our 2 here.
N is the embedding space, M is the manifold, like the vector space of where the local chart maps to.
Yeah. Okay, I think we're all set.
Good. So now I have to get rid of all the pink. Just a second. All right. Then density on manifold. So the question is now, of course, how can we use this now to define something like a flow in a manifold? So there we can now plug together what we learned so far. We can, so this is if we have the manifold M here, and basically now say we have a diffeomorphism between the two manifolds. I mean, this is just the classic diffeomorphism. We can think about what does it mean like to use this implicit density that we had here and push it forward using such a flow on the manifold. And what you can do is very much as before, you basically write down the density on the manifold. Now we just push in between the Jacobian of this transformation. So it looks very similar to what we had here with the Kramian for just going to the charts. But if we want to look at the density of the flow, it just means like we plug in this n by n, so the full rank, so the basically the embedding space Jacobian of this flow between the two chart embeddings. We sandwich that, and then again it's an m by m matrix. So since it's a diffeomorphism, you can prove that this flow transformation always has rank between m and n. And yeah, by that basically you end up with a formula for what does the volume change from transforming from this manifold to this manifold by this red thing. How does it change the actual density that you initially had on your manifold? So this is again, this is the chart formulation. So if you go to differential geometry, you can make this all much nicer, then it becomes much easier, but also it requires basically a full-blown lecture on the way how to actually write this down. So this is the coordinate way of writing it down. So questions on this so far?
Yeah, please unmute.
I guess my question would be, if you have several charts, basically you have to stitch together several charts, right? So
yeah,
how do you deal with that?
That's the beauty of doing it in differential geometry, because there the charts don't matter. Here we just have to believe that picking the chart for this volume formulation here does not matter.
Whoa.
Sorry?
Yes.
So what I mean is like the definition is independent of the charting that sorry.
I think the question aimed into another direction.
Okay.
Not that we have multiple possibilities of charts, but if we have, okay, now maybe I'm getting this wrong. But if we like want to compose charts with each other.
I think it is kind of equivalent. So what you would say, like in general sense, you would say, it does not matter what input chart I pick or an output chart I pick, basically from my point here and my point here. I should always end up with the same volume formula. And this is like, it sounds unintuitive if you write it down in matrices and stuff, but it follows if you write it down in the classic abstract, like the Riemannian geometry, where you try to be coordinate free. In the coordinate free version, it directly follows. Then if you bring in the coordinates, then you can show that whatever, I don't know, you can even rotate your vector space in the output side or whatever, the volume doesn't change. This is just a, let's say like a consequence of the differential geometry.
Right. Thank you.
You could also say, like, if you modify the chart, it means like you have something like a rotation or whatever happening on this thing and this thing, and they cancel each other out. It's like an analogy. It's a little bit rude, I'd say, but more or less the analogy that you have here. Yeah, so bottom line, this is how we could actually write down the volume change for flow on a manifold. Okay, at this point we have nice tool. So in principle, we could now, I don't know, say this is SL3. This is any kind of flow transformation that we don't know what it looks like on SL3. Mapping to SL3, we can use this formula. Probably there's some annoying numerics involved here, but in principle, we can know what to do. We can make it even nicer now. So the next thing that I have to introduce, sorry for all the math, is so-called covering space. So covering space is a concept actually from algebraic topology, which is super useful to know. So it is basically telling you like a relation between spaces that are not homeomorphic, so they are not the same, but they share a lot of structure. And some of them, for example, is the so-called covering of a circle. So again, if we take the circle, then we have to, and we take basically a map, in this case, the exponential map, which is just mapping a real number onto the circle. Then you have this cool property that basically for every point on the circle, there is a neighborhood U, which is then, if you go for the pre-image of this map, is repeated over and over again. It's a nice property. It's basically called a covering. So if you think about this as the real numbers, and you wrap it around in a spiral and you project it as a shadow on the plane, then the corresponding figure would be a ring. And the important property that you get is this one. It's basically telling you the pre-image of this projection is of any open set around this point is basically, again, the open set times, for example, set, which means like you just have discrete different pre-images. And in general, you call this a covering space. So if basically, oops, I have to remove this. So if this property holds and this thing is something discrete, then you call it a covering space. And the cool thing about covering spaces is that they allow us to generalize a little bit the change of variable rule that we know for like going. So here we saw it going from one manifold to another manifold. Before we just knew it only from real spaces to real spaces. We can go even beyond different manifolds. So if this is like one manifold R and this is another manifold S1, they are not the same. I can still write down the volume change because of this property as now just becomes like a discrete sum over all these different pre-images. And then I locally have something like a diffeomorphism that tells me how the volume changes. So locally, it's again something like a normalizing flow. But now I have to sum up over all these contribution of the pre-images. And yeah, if I do this, then basically I end up with this nice formula that tells me sorry?
Okay, and if we now have our, we now have our double cover, then we also have to do the addition, but I thought we had to do a multiplication where the Jacobians cancel out.
This is, we'll talk about in a second. Just first off, this is the prerequisite for this. So what we do is basically we sum over all the possible pre-images, the red ones here. And then locally, we just have a diffeomorphism where we just do normalizing flow. And this again, this thing again is just the Scramian from the from here. So this is basically the rule of how do we get a density, for example, from R, where we easily have a density onto S1 and make sure that we actually get all the pre-images. This is called a covering space, and this is what I would call a covering flow. And now we use this construction for our SO3, because SO3 is nasty. So you have matrices with a determinant constraint and so on. It's super annoying. It's not so clear how you formulate a flow. So what you can do, and this is now where some beautiful math hits in, which is called the SO3 double cover. So first of all, we can look into the sphere in 4 dimensions. So basically all the vectors in R4 that have length 1. And another way to look at them is so-called unit quaternions. And so quaternions, I don't know, is everyone here familiar at least with the concept of a quaternion? So what it means?
Well, why is that even necessary here? I mean, we just have our 4-dimensional space, and we have all the unit vectors in that, and we just...
like at this point, we don't need anything more. But after that, we need more. This is why I'm asking.
No, I'm not. I heard about quaternions. I know they're somewhat similar to complex numbers in some sense, or an extension of complex numbers, and they have something to do with rotations. But all I know now what they do with rotations is that for every rotations there's the minus quaternion and the plus quaternion.
Yes.
And that correspond to this rotation.
So you could say quaternions are just like 4-dimensional vectors. So if you write down a quaternion, you could say it's A plus, good. Now I have to. So this is A plus I times B plus J times C plus K times D. So similar to a complex number, just now we have 2 extra terms. And we just multiply them as we would multiply complex numbers. And the important property is now that we basically require for all of those guys the same thing as for the complex numbers.
Mm-hmm.
And then gets a complicated product. And this is the so-called non-commutative Hamiltonian product. So in contrast to complex numbers, for complex numbers, it's commutative. So if I have C1 times C2, it's the same as C2 times C1. But for quaternions, this is not the case.
Okay.
So if this is this Hamiltonian product, then in general, this is not true.
And what does it now mean to take the conjugate?
The conjugate means it's basically saying instead of the plus for these, let's call it hyper-complex part, basically the part that is where you have these other complex terms, you just flip the sign. Similar to what you do in a complex, right?
Yeah. All right. And now our ABCD corresponds to our x1, x2, x3, x4, and
exactly
to embed.
Exactly. So and this is what the quaternions are. And then basically there is a product on them, which is this Hamiltonian product. So taking 2 quaternions, you can get a quaternion using this rule. And now we look at the special subset of them, which are the unit quaternions, basically the quaternions of length 1. Okay?
Yeah, I think we're eager.
Good. So they don't have a good sponge tool here. Okay, so now let's look into some things to understand why they're useful. So the first part is that we can look into is the so-called embedding. I call it iota. It's a math way of calling it. So you start with the real, with a 3D vector, like, I don't know, just any kind of vector in 3D that you want to rotate. And you can just embed it into 4 dimension by just setting the last part 0. This is just a so-called canonical embedding.
I think these are the easy parts. The projection just means removing the x4. And now what do they
exactly? And then the corresponding projection is we are just basically chopping off some part in the back. And now the rotation of a three-dimensional vector around a unit quaternion just means we first embed the vector into 4 dimensions. So it becomes something like this. Then we apply the quaternion from left and right using this Hamilton product. And then we project back to our vector. And this is a rotation. You can show this basically corresponds to rotation.
I think all of that was very excellently explained in your paper, except you didn't say what the conjugate is. But I mean,
okay, sorry.
Quaternions, then
we just assumed that it is in any introduction to quaternions. It's given. Okay. So this way we basically get a mapping from a quaternion to a rotation. And in fact, you can even go the other way around. So I don't explain this, is a bit more complicated, but you can also always, for every rotation, show there's a quaternion corresponding to it. And in general, you end up with a structure that I try to draw down here. This is the so-called double cover. So if we say the quaternions, they're a sphere as discussed, so I draw them as a circle here. So if you have a quaternion Q, then as I said, this corresponds to a rotation on the SO3, like a semicircle is drawn here. And for each of the rotations, there's basically the possibility to correspond to this Q, as we said, but also to minus Q, which corresponds to the same rotation. And the reason for this is basically if I have a minus here and a minus here, this will cancel out. So it corresponds to the same rotation. And this is what people call the double cover. So if we go to the covering space, so here we had many, many covers, like set in total. And now we have something, this is just a bad analogy, but just a 2 cover, where we only have 2 pre-images for each point. But it's the same idea. Okay, clear so far, or questions?
I think we're pretty good.
Good. Then let's go to the recipe. So the recipe now is clear. So the idea is, okay, getting a flow here is nasty, or will not be smooth, or needs weird ways to cut it open, or Euler angles, or whatever we don't like. So why not just define it on the hypersphere, where math is much easier, and then try to actually push it over to this SO3, basically by just summing over the 2 pre-images that we have on the quaternions, right? So you could say we have SO3, we go to the quaternions, we go to the quaternions, we do some flow stuff here, we go back. So far so good. The problem is just that for each n of the n rigid bodies that we have, for each of them, we have to sum over these two contributions here. And now, of course, if you sum over all of them, then you have 2 to the power of n different contributions. And then it's clear that this way will not work for anything non-trivial. So the basic recipe is clear. It's in general a nice idea, but we need more. This led up to the, sorry?
That point I also didn't get. I didn't get why we now can't just do both. But yeah. What
do you mean? Both?
I didn't get why we can't just sum over the contribution.
We can, but we can. So we have to sum over but now we have to sum over all possible configurations. And if you think about them basically as +1, -1, and you have n of them, then you are basically summing over all possible vectors, assigning.
Yeah.
You have to sum over all possible vectors.
And now that's why you wanted the sign-equivariant architecture, right?
Exactly. This is where I'm heading to now, because you want to avoid doing the summation.
Do you know the sign and basis net paper from Derek Lim and Joshua Robinson?
Yes, we talked about already.
Okay.
Yeah, unfortunately, it does not help in this context. I will explain in a second.
Yeah.
But yeah, so this is the sum that we have to take, and we don't want to do this. So let's not do this. And in order to not do this, we go to sign-equivariant flows. And sign-equivariant flows is the same idea as before. We just say we have a flow from S3 to S3, but now we put a constraint, which is if we flip the sign for the input, then the sign flips correspondingly for the output. And the cool thing about this is that we just know that then the contribution of each possible pre-image here, so the Jacobian contribution, is totally identical, which means instead of summing over the whole thing, you can just cross the sum and just multiply it by 2.
Okay, I got it. But then now this is the cool thing, but the not so cool thing is that now we're restricted in the class of function, or it's tricky to come up with a normal.
Exactly. So we don't, like, first of all, we already struggle with having these flows. There are some flows, but I mean, in general, there are just not so many of them. But as you say, yeah, exactly. We are also restricting this class.
Okay, and then in your experiments, right, you have one experiment where you only consider a single rigid body, like just a methane, and there you could still do the summing. Have you tried doing like a typical flow that's not sign equivariant there versus your sign equivariant and doing the summing and seeing how much of a difference it is?
Actually, I didn't. It's a good point. I mean, there you could have done it. You're right. I assume compared to the more powerful one we have, it wouldn't be too much compared to the Moebius one. Maybe I explain it after we introduce the transformations, then it's easier to talk about. But yeah, I will come back to that. All right. So we have the sign equivariance. So as I said, the contribution of each one is identical, and then it means we only have n summation terms, basically one for each body. And then there's a very cool result. This is important. So because you said in terms of the restrictions that this is actually a restriction. So together with Pim, I thought long about it, and actually we believe it's not a restriction because we don't care about general maps between quaternions. We only care about the action on the rotation group, right? And the fun thing is that you can show the following. So if you take any kind of map that goes from SO3 to the quaternions, so any kind of embedding, you could say, which only has to require that if you go back via the projection, it's the identity. It's the only thing that you need to require, but could be anything. Then take any sign-equivariant flow, then you can always do this. So you can always end up basically with a flow that you define by first going with the embedding, doing the, sorry, this is missing, doing the actual flow, and then going back with the projection.
Okay.
And the cool thing is it does not matter how we do this. This is fascinating. It just doesn't matter. You can just take deterministically one of the signs, you can just randomly sample them. Does not matter. It's just important that you satisfy this.
Okay.
And in that sense, you can even show that if you have this condition, you're not restricting yourself when you just want to study flows on this one. So technically it's not a restriction. It's just a question like if you can write down a cool architecture or whatever, but it's not a restriction in a mathematical sense. All right. Then, yeah, let's quickly talk about the implementations, then we can discuss the two results and the stuff that you asked. So the first implementation that we had was basically an extension from Danilo Resende's work on flows on spheres and tori. There was one interesting part in it, so-called Moebius flows. So the idea is for any hypersphere, you can project a point P by picking a point Q within the sphere, sending a ray through them, and basically cut it with the other side of the sphere, getting P prime. This is the so-called Moebius flow. And this works in any dimension, and the cool thing, it has a closed form, it is has a tractable Jacobian and everything. Only downside is this by itself is not flip equivariant. And this is what we now came up with, is basically making like a double Moebius flow. So what you do is you do Moebius flow for one Q. And then you do the Moebius flow for minus q. So you get 2 points, P1 and P2. And then you take the average on the circle of these two guys. And you can show this is a diffeomorphism on the circle, which is quite surprising. It has an analytic inverse that you can compute, so no numerics that are crazy. And you even get an analytic volume change, so you don't have to do all the tangent space and the Jacobian stuff that we saw in the beginning. So you can just closed form write down what's the volume that's changed, like a real MVP.
Isn't there anything tricky about, like, this seems hard to reason about. Oh, wait, does our network even have to reason about?
Our network basically has to predict the Qs here. Takes one Q and then the minus Q you just plug in. So it just has to predict this vector basically.
Yeah, no. I think it's, yeah, good.
I mean, if you want to see the details, we have also just uploaded the code to GitHub. So just look into the code base. I mean, what we basically do is we predict this Q. It's a 4-dimensional vector. We just normalize it to be in the circle. And then you just do this projection.
Okay, so your flow also just goes from any Q without any restrict. No, well,
No, the flow basically takes P and maps it to P prime. And the map doing this is conditioned on something, yeah? And this conditioner, what it actually does, it predicts a Q, it's called a Q tilde, which is generally an R4 vector. And then we have something like Q is Q tilde divided by the norm of Q plus some epsilon or whatever.
Yeah, but you just, so your flow can sort of produce infinitely many values that are mapped to the same value. Because you normalize.
I'm not, oh, wait, do I normal? No, I do something else. Let me think. How do I do it? I map the Q tilde to no, I don't, because I don't exactly normalize. I do something like, let's call it, for example, this. Yeah. So what does this maps from the real space into the open ball? If Q goes to 0, this thing goes to 0. If Q goes to infinity, the whole thing goes to 1. Yeah.
Yeah.
So what you get is basically like a map between the open ball. So you don't get the surface and the real numbers.
Yeah. Okay.
And this is how you can parameterize this.
Yeah. Good. And then to the good map, the one that actually works.
Actually, this is working. I don't know why you're complaining. This is the one that produces the crystal results. It's working pretty very well. It's working excellent. I'd say this is the one I would trust in practice, actually.
Okay.
because of the numerics. The numerics are super nice. I mean, it has a closed form. It's super fast to compute.
Okay. Yeah, I thought I just looked at the images for the for your methane and saw
No, it's a trade-off, but we can discuss it like so. If you look into the results, so it's a trade-off. So this is one you could say it's like real MVP. So it's pretty stable, pretty clear what it does. Has an analytic inverse, analytic volume change, and so on, right? So but it comes with the caveats of it's by itself. It's not super expressive. So for multimodality, you have to find ways.
Okay. Yeah.
But it's like real MVP basically. Then the other thing, these are the convex gradient maps. So here we basically figured out that if you take like any strongly convex function and you look at the normalized gradient of this function, and this was actually surprising to us. This is actually a diffeomorphism on the sphere. Super simple, we didn't notice. The problem is a bit, so this can be super general, right? So this can be any input convex neural network or anything. But it comes at a price. The price is that now the inverse is not analytic anymore. So you need to employ a solver, like a fixed point solver, for example, in order to get the inverse. And also the volume change is not in closed form anymore. So in order to compute the volume change, you literally have to brute force your way through this guy, which in 4 dimensions is not unfeasible, but it's of course still numerically not so nice. And yeah, in practice, we realized you can make a very simple implementation for the whole guy, which is basically just, you could say, an MLP. So what you do is basically you transform the input with an arbitrary weight matrix of k outputs. You send it through a strictly convex activation. So here we use the log of the hyperbolic cosinus, which kind of looks like this. And then we take strictly positive weights and multiply it with that. It's basically, you can prove it's strictly convex. And then, yeah, it's a way to parameterize this. And if you increase k, you get as many bumps as possible.
Mm-hmm.
Yeah. So, and this, of course, is in one shot, you get a very multimodal complex transformation, but at the price of this stuff.
Yeah.
So this is similar to like making a mixture of I don't know what was like a mixture of sigmoids, for example. You can also write this down as a flow. Then you get these very nice multimodal densities in 1D. But the problem is to invert them, you have to do a fixed point iteration.
Mm-hmm.
And you have a similar situation here, just in higher dimensions. And then basically you can see the trade-off. So you either go for the real MVP solution. So this is the real MVP. And oops, now I closed the window. Why? Oh, no. And this is the convex gradient map. This is more like, I would say there are these convex potential flows, if you know about them. So this is basically the real space analog to our spherical case here. And then, yeah, as I said, there's a trade-off of which of the two you want to use. Okay, and then for the final plugging things together. So initially we studied rigid bodies, right? So not only the rotation. So you can now take this rigid body transformation, this T. You can take any input embedding going from the rotations to the quaternions. Then we can take any of our flows that only has to satisfy its equivariant according to the quaternion sign. And if we plug everything together, then you can show this is a valid rigid body flow. And the cool thing is also you only have to compute the volume for this transformation on this guy, but you have to make sure it's on the manifold. So you have to use these rules before. Okay, that was the theory. Maybe we can just quickly dive into the results. So for the results, we just studied 2 things. So the first thing that you already mentioned, Hannes, is, so you see the paper open, right?
Yeah.
All right. So why is it? Yeah. So the first result was we basically just studied the expressivity in terms of multimodality, because as I said before, there's usually with real MVP the problem that it's not so easy to get multimodal densities. And for this, we just used this methane-like thingy with an external field. So basically it has a bunch of modes where it gets fixed. If you project it onto the quaternions and you basically look how it looks like, you see it's quite multimodal. So the first row is the data distribution. Okay, y is, sorry. And then if you go for, so like the competing method that we looked into was another formulation for flows on the quaternions, which is basically using like an affine map and then normalizing an affine map. And then you can see this cannot really learn a lot. So it basically learns one bump, even if you stack multiple of them.
No, can you, I got lost there a little bit. What is this affine baseline?
The affine map looks like this. So it's basically taking a quaternion and mapping it on this guy.
Okay.
And it's similar to the convex flow, just much less expressive. You could say the convex flow is a generalization of this, because the convex flow could, like, you could write it down as a convex flow for Q.
And it's not sign equivariant, right?
This is sign equivariant.
What?
Because, I mean, linear map is sign equivariant, right?
Yes.
I mean, it must be sign equivariant because you can prove it's basically the gradient of this thing. So it's a subclass, you could say, from the convex flow.
I mean, we can see if we put in our minus in our Q, then what comes out, you have WQ, which is still negative.
It is a linear function, and I mean, by definition, scalar should factorize through it. Exactly, but these are the affine ones. And so if you use those guys, and even if you stack them, I mean, then you get a multimodality structure of basically this. So it's not really multimodal at all. For the Moebius, the more you do, the better it gets, but still, yeah, similar to real MVP. Like if it's really multimodal, you have this problem that it basically the modes stay connected, blah, it gets like the bumpiness, but you don't really get rid of the mass between the modes. And for the convex ones, this is basically where we said like they are kind of expensive, and numerically the ones that are not so nice for inverting and everything. But for actually resolving multimodality locally, you can see they're essentially perfect. So you just increase the number of K, and the better you, so we have it in the appendix, I think. So if you increase the number of K, so for small K, you can see it's limited. The more you add, basically it converges to the actual thing. So this was just for like studying the trade-off between the two possible transformations. But of course, now we want to actually study molecular dynamics rigid bodies. What we looked into here is basically ice crystals. So let me make this a bit bigger. So the ice crystals here are basically a box with water frozen, and it has a fixed tetrahedric structure. And the ice model that we here have is like a kind of a standard model that we put in a certain crystal that is stable. And we study it at different temperatures. And so very important here, there are no crazy conformational changes. So it's not that we have like two crazy disconnected modes or something like this. For now, it was simply about, are you able to fit the density at all? Which is not trivial actually. So if you just naively go from one temperature to another, then you can see there's basically no overlap of the energies. If you go to the larger system, it's like quite big. So this is normalized by the number of particles. So this is actually a quite big energy difference. And so the idea is basically you cool down the system, but in a concerted way, so that basically you don't make crazy moves. And so what? Okay, I'm actually not. So what you do is basically you simulate the system on. So where is it? Yeah. So you simulate the system on one temperature. In our case, it's more or less room temperature, where the system converges very quickly. So I don't know, easy to sample. And you try to learn free energy perturbation between this room temperature, and then we had one thing with, was it, I think 100 Kelvin, and one thing with just 50 Kelvin, so it's super stiff.
And Jonas, do you do the thing with the auxiliary variables here as well?
No, here we don't. We just basically make a coupling between the translation and the rotation, right?
And do you train with energy here? No,
this is all energy. This is learned free energy perturbation. This is the Bernsberger.
Okay. I mean, the question doesn't really make sense here, right? Because we have a complicated distribution, and we're basically like training with data means the same thing as training with energy here.
Sorry, excuse me? What?
If we go from high temperature to low temperature, and this is the map that we're learning, then training with energy is this. There's no distinction between training with energy versus training with data. You take a sample, you flow it back, and you evaluate the density. Or you take a sample from the other side, you flow it forward, and you evaluate the density.
Exactly. This is why I'd say learned free energy perturbation is not exactly the same as a Boltzmann generator.
Yeah.
It is really learning like a mapping between the two equilibrium densities in order, for example, to estimate the free energy between them.
And here in your experiment, why do we need to look at a larger unit cell, so to say? Like why?
It's because like the free energy grows, for example, with temperature, but also with system size. So the estimate becomes more difficult the larger you get or the colder you get. This is why we have the basically reference. Compared to the reference, we make the system colder, or we make it larger and compare, and it still seems to get quite reliable results.
Okay, now I was confused because I thought we had some periodic boundary conditions here.
We have periodic boundary conditions here, yes. But it doesn't mean like if you go a smaller and larger system, there are boundary effects, right? It's like with an Ising model. If you have an 8x8 Ising model, it behaves differently than a 128 by 128. Just because the boundary effects accumulate and then you get different thermodynamic statistics.
Yeah. So it's better if we have the 100 by 100 is a more accurate
representation. If we go to infinite, if you really want to study real world water, then we have to basically have all water molecules exist. But I mean, yeah, at some point we have to make a cutoff.
Yeah.
And that's actually what we explore basically the two components, either like the bridge gets very large because temperature difference is large, or you go to bigger systems that are non-trivial. And as you can see, we can get it up to reweighing accuracy. So this is something we have not been seen with Boltzmann generators before, to get for such a big system to get basically reweighing accuracy. So we get like effective sampling size that's not trivial. Yeah, and exactly. So the water model by itself, it has rigids. So there would be no other way to actually map to this system, because you just need a flow that's intrinsically defined on this manifold. Yeah. And then going beyond that, of course, there's something we didn't try because it was also a bit beyond the scope of the paper, is that, of course, like the internal degrees of freedom, we just kept them fixed. But it's, of course, very reasonable if you study protein, for example, and you say the rigids are the amino acids, for example, that you can say you also model these internal degrees of freedom, but you consider them to be very simple. I don't know, just local Gaussians or whatever, if they're just the bonds. That you decouple the problem of like predicting the macrostructure of a protein using the rigids, and then predicting the internal structure using the internal coordinates. But yeah, we didn't experiment with it here, but it's very reasonable to think about something like this for future stuff.
Okay.
Yeah, so took longer than expected, but yeah, was also a bunch of stuff.
Cool. Then, for example, for your water, this would be much harder when we do it with liquid water, right?
This is a very good point. Yes, for many reasons actually, because it's not only, so I think the flow that we have here would still be a building block, but you run into another issue, which is how do you actually sample one shot without collisions? This is like an orthogonal problem that I actually wanted to do a final paper on during my PhD, but didn't make it because yeah, not enough time for everything. So I guess you need another flow architecture for this, basically one which can one-shot sample conformations without clashes. So because like if you don't have this, then here we basically start from something that is already crystal and map it to a similar crystal, just a stiffer one or different, little bit different statistics.
Yeah.
So this is, of course, kind of clear because we know where the things are. So it's more about learning the correlations rather than crazy movements. When you want to sample like total unstructured noise and shape this into, I don't know, Lennard-Jones crystals, you really have to learn the correlations of not clashing into each other. And this is a much harder problem, of course.
Yeah, sure. Oh, but what does this now have to do with liquid? Well, if I want my liquid that's 300 Kelvin versus 350 Kelvin, I want the free energy difference there. Then why, like there, I also just have to map local changes to the orientation, right?
Yeah, it depends. Okay, so if you want to do free energy perturbation, yeah, you probably don't have the challenge as much as here. You have it if you want to do Boltzmann generators or something like this, then it will be hard. For free energy perturbation, there is also a challenge, which I guess, let me think about it. Yeah, so what we didn't study here, what I guess you would need to do for liquids is that you need local equivariance, so-called gauge equivariance. Basically, you need something that, so if you have a local system in a liquid, it can be arbitrarily rotated relative to the rest. And you have this reoccurring all the time. So without gauge equivariance, I guess it's a much harder learning problem to figure out what's the kind of right relative rotations. So you could easily combine this with a framework. It's just you need to, so for example, if you take the convex potential flow that we have here, you need something like a gauge, like a local frame. You would always have to rotate it to this local reference frame, then apply the flow, rotate it back. But it means like you have to propagate kind of an auxiliary frame for each of the molecules. Yeah, we thought about doing something like this, but in the end, just didn't have the time to do it. So I think this would be definitely, if you want to do something like this, one critical part. But the other critical part, I think, is really avoiding atom clashes, which I think is another big challenge if you want to go to liquids. Yeah. Because in a crystal, you know that basically atoms have a certain order, and they don't do super crazy stuff. In a liquid, I'd say if you go from, I don't know, 300 degrees to 0 degree in water, there's a lot of structure differences happening, and I think this is super hard.
Yeah, so it's just because there's more liquid, there's more flexibility, so to say, and modeling all that flexibility or the
so like a crystal just is more, as the name says, it's more structured, so you just know already a lot more. And you have less to learn. For water in liquid phase, it's just crazy chaotic. And I think this is just the next challenge. Initially, we wanted to tackle water, of course, but we chose crystal water first because it seemed to be the next step beyond like monoatomic water, what Peter Wensberger did. I guess liquid would be the next challenge. But I mean, even this is already quite interesting. So I'm not too much into this, but my collaborator, Köhler, so he's into materials, for example. So he says there's a lot of interesting applications. Also, if you just go to molecular crystals, which are not water, but not protein related, but more like in, I don't know, certain, battery cells or whatever. He said like there are a bunch of applications where this matters to just simulate the free energy difference between two different crystal states. And so for this, you could use it already. But for the grand goal of sampling water, I guess, another 1 or 2 PhDs in between.
Okay, well, but then I think that's a good note. Like they're talking about real world applications and where is it useful. Maybe to finish today, we can have your estimation on where the field is at now in terms of targeted free energy perturbation and learned free energy perturbation, in terms of what sort of real world applications our flows can now already have, and what is the next level.
I mean, real world is always a thing, right? So if we talk about going from in silicio computations to in vitro stuff, I think we are still magnitudes off, right? But it's also not only holds for flows, but probably also for diffusion models and whatever. If we look into computing certain quantities that are otherwise super difficult to compute, I'd say it depends a bit on the niche, but in certain niches, we are already at this point. So for example, I'm not too much familiar with his work, but I just know from Michele, people like Andrea Rizzi and others, they are already using flows to compute, for example, free energy difference for systems that are otherwise extremely difficult to tackle. So the traditional way is usually you have this EMBA methods or whatever, where you basically simulate for each, like you split the temperature or whatever you have, like the path and the Hamiltonian, into k chunks, and then for each chunk you simulate something, and you need enough overlap, and then you can estimate the free energy difference between. And you can always find systems where this becomes extremely hard. And if you want to compute a phase diagram for all the different states, for example, and get to the free energy differences between all of them, there are enough systems out there that are super difficult even for smaller scale. And I'd say flows are already at the point where, for this niche of scientific understanding, they can already provide value. But I'm too far from applications to actually judge this. This is just third-party knowledge.
Okay, thanks to Jonas for presenting his work on his normalizing flows on SO3. And yeah, if you want to join future reading group sessions yourself, all the information is in the description. See you next week.